lines. Now if this is the phase diagram, on the left hand side of these two lines is solid. In between these two you have liquid. And on the far right, these are all gas. So that's what we need to know. First, the composition of phase diagram. So if you select any line or any curve, this curve has solid on the left side, gas on this side. So that's sublimation, solid-gas equilibrium. If you think about this straight line, solid on the left, liquid on the right, that's melting or freezing, solid-liquid equilibrium. Going from here to here, on left side of this curve you have liquid, on the right side you have gas. So it's dealing with liquid-gas equilibrium or vaporization. Now we need to understand what is normal boiling temperature. If outside pressure is 1 atmosphere, let's have 1 atmospheric line here. So if it's 1 atmosphere, draw a line here. Liquid-gas equilibrium would be given by this, and that's the boiling temperature. This is boiling point, where there is a liquid-gas equilibrium under 1 atmospheric pressure. So if I give you this kind of graph and ask you to get boiling temperature, then this is going to be the value. For melting, this is going to be the temperature. This is melting point. Solid-liquid equilibrium. So make sure you know this. And this is called triple point, where solid, liquid, and gas are together. So you need to know what triple point is. Solid, liquid, gas, all together. That's here. That's called triple point. And this curve goes up to what is called critical point. This is called critical point. And corresponding temperature would be called critical temperature. So critical temperature is the highest temperature when you can expect a liquid. Beyond critical temperature, there is no phase diagram, they will be all gas. So that means you cannot condense a gas to a liquid if the temperature is higher than critical temperature. So that's all that you need to know from phase diagram. And the next one that I would like to go over is intermolecular forces. Intermolecular forces. If you look at my lecture note, I mentioned about different types of intermolecular forces, like ion dipole, dipole-dipole, hydrogen bonding, polar bonds, ionic bonds. So all those are different types of bonds. Now, in particular, we are going to focus on London dispersion forces and hydrogen bonds. London dispersion force is present almost in every molecule, but is predominant in some molecules where no other types of interactions exist. Say for example, it's a non-polar molecule, then London dispersion force. Now if it is a polar bond, a polar molecule, it would be dipole-dipole interaction. Now we need to know in what cases we expect hydrogen bond. When hydrogen is bonded to, in lecture note also mentioned that bonded to oxygen, nitrogen, and fluorine, then you'd expect hydrogen bonding. These are pretty strong bonding. Like in case of water, you would have hydrogen bonding like this. And even though water is a pretty tiny molecule, its boiling temperature is pretty high. It's 100 degrees centigrade. So read this carefully. And by the way, London dispersion forces operate when there is a nonpolar molecule. So you can pick any nonpolar molecule and you'd expect London dispersion forces. For example, if it's a CH4, this is the nonpolar molecule because they all, this is sp3 hybridization, tetrahedral structure, they all cancel out and then it's a nonpolar. And of course here hydrogen and carbon are pretty small difference in electronegativity. So that's why also all these alkanes are almost nonpolar. You can consider it to be nonpolar. So this is nonpolar, so between alkanes and one alkane and another alkane molecule, the interaction would not be hydrogen bonding or any other types of bond. Only type of bond which is going to operate here would be London dispersion forces. So between them, there's a weak force, there's a London dispersion forces. And that's why methane, this is a natural gas. It's gas at room temperature. So read this carefully. So whenever I see any nonpolar molecule, I'd expect London dispersion to be the major type of force. If I see hydrogen bonded to oxygen, nitrogen, fluorine, I would expect hydrogen bonding. If I have a polar molecule, it's a dipole-dipole interactions. So read this carefully. And the very last thing for this review would be, this is coming from what we call Le Chatelier's principle. And that's the only part that would be on the test from this chapter. I think this is chapter 15. So applying Le Chatelier's principle in this molecule, I think I picked this problem from chapter 15. This is number 61. 2SO2 plus O2, that gives 2SO3 gas, and question is saying that delta H is negative. Negative means, or less than 0 is negative, means exothermic. Exothermic means you not only get products, you also get heat. So let's write down heat as on the product side. That would help you to answer these questions. So in this problem, they're saying that what's going to happen if oxygen is added. When oxygen is added, this is how it works. Le Chatelier's principle. This is in equilibrium. First, assume that system is pretty happy with all its concentrations. That's equilibrium. So Le Chatelier's principle says that if you disturb that, now you can cause disturbance in many ways. One way is to, in this case, adding oxygen. So when oxygen is being added, then you should try to get rid of this extra oxygen. So how can I get rid of this extra oxygen? By forcing this reaction to happen from left side to the right side. So reaction has to be moving from left to the right. At equilibrium, neither direction is favored. So this is, your disturbance is going to cause it to go from left to the right, so that some of these oxygens are used up by combining with SO2 and giving this. So left to the right, the reaction will be favored. Or sometimes we often say that reaction towards the product will be favored when oxygen is added. I'll stop after going over the next one. Heat being added or heated. Heated means you are adding extra heat. Heat is like a product here because this is an exothermic reaction. You are adding heat, it was happy with all the heat it had. So extra heat is like a disturbance to its equilibrium. So to try to get rid of that heat, extra heat. So if it goes from left to the right, you generate more heat, so that doesn't help. But if it goes from right to the left, it uses up the heat in combining, in reacting with SO3, and which would break down into SO2 and O2. So reaction favored from right to the left. So read this carefully, and that way you're not going to make any mistake. So this is the conclusion of my review for exam 5.